This video is part 3 of our lesson on basic differentiation. We're going to start with finding the equations of tangent lines. So for this first example, our function is -2 cosine x plus 5. We want to find the tangent line at the point x over 2, 7. So that gives us the x1, y1 that we will plug into our equation of a line in point-slope form. And now we need slope, which we get from finding the derivative. The derivative of -2 cosine x is -2 times negative sine x plus 0, because the derivative of 5 is 0. So we get +2 sine x. If we want the slope, we need to evaluate this at our x value, which is pi over 2. So we get 2 sine of pi over 2, and sine of pi over 2 is just 1, so our slope is 2. So now we have everything we need to plug into our equation of a line. So I get y minus 7 equals 2 times x minus pi over 2. And if we want to go all the way to slope-intercept form, I will distribute this 2 and add 7 to both sides. Okay, here's another example. In this case, our variable is t. So I've written the equation of the line in terms of y and t instead. So our point here is actually t1, y1. And we need to find the slope by finding the derivative. So we take the derivative of -4e to the t. Well, -4 stays out front, and the derivative of e to the t is e to the t. So our slope then is our derivative evaluated at 1, so we get -4e. So we want to put that into our equation of a line, so I get y minus a -4e will be plus 4e, and I got that from here, equals -4e from our slope here, times t minus our t1 is 1. And if I want to keep going, then I will distribute the -4e, and I get -4e times t plus 4e. And if I subtract 4e from both sides, then we just get y equals -4e times t. Okay, here's another example. I'm given a point, so that will be my t1, y1, since our variable's t in this instance. And we'll take the derivative so that we can find our slope. The derivative of sine is cosine, and the derivative of 1/2 e to the t is 1/2 e to the t. So our slope then will be our derivative evaluated at pi, and cosine of pi is -1, so our slope is -1 plus 1/2 e to the pi. That's ugly, but it's just a number. So we can plug that in to our equation of a line, and I get y minus 1/2 equals -1 plus 1/2 e to the pi times t minus pi. And if I want to keep going, although this is a perfectly good equation of a line in point-slope form, it's going to be a little bit messy just because these aren't pretty numbers to work with. but I can go ahead and distribute this. Negative 1 times negative pi would be plus pi. And then we'd have minus pi over 2 e to the pi. And we can add 1/2 to both sides. And that would give me my equation in slope-intercept form. Okay, our next set of examples asks us to find horizontal tangent lines. Horizontal tangent lines have a slope of 0. So if I ask you to find all the points where the graph has a horizontal tangent line, what we want to do is find the derivative and set it equal to 0 and find the values of x that make that true. So the derivative of x cubed plus x is 3x squared plus 1. Then we want to set that equal to 0 because that would be the slope of a horizontal tangent line. And we're going to solve for x. And I get negative 1 equals 3x squared. Divide both sides by 3. And I get x squared equals negative 1/3. And if we take a square root of this, I'm taking the square root of a negative number. That gives me an imaginary value, and I cannot plot an imaginary value in the xy plane. So nowhere on the graph of x cubed plus x is there a case where I would have a horizontal tangent line. So there are no points for this curve. Okay, but let's try one that is going to have some points. First, we need to find the derivative, and the derivative of x squared plus 9 is 2x. Then we set it equal to 0. And if we solve for x, well, we just divide both sides by 2. We get x equals 0. Now, when the problem asks me for the points, it's not asking for just the x value. It wants to get the actual x comma y coordinate. So my x value is 0. I need the y value to go with it. So I plug my x value back into my original function, and when we do that, we'll get a y value of 9. Okay, let's try another one. The derivative of this function is 1 minus 4 e to the x. If we set that equal to 0, I can add 4e to the x to both sides, divide both sides by 4. I get e to the x equals 1/4. And when we want to solve for an exponent, we take a log of both sides. So I get natural log of e to the x is natural log of 1/4, which natural log of e to the x is just x. So I have my x value. I need the y value that goes with it. I get the y value that goes with it by plugging this back into my original function. So we're going to get a y value of natural log of 1/4 minus 4e to the natural log of 1/4. And that's going to simplify to negative 4 times 1/4. So our point is natural log of 1/4, natural log of 1/4 minus 1. All right, one more example. So we want to find the horizontal tangent lines. We need to take the derivative and set it equal to 0. The derivative of the square root of 3x, well, square root of 3 is just a constant multiple. Derivative of x is 1, so we get square root of 3. Derivative of cosine is negative sine, so this is going to give me negative 2 sine x. So if I set that equal to 0, that will allow me to solve for the x values that give a horizontal tangent line. Add 2 sine x to both sides, and I'm going to divide by 2. I get sine x equals the square root of 3 over 2. Now, we need to find the x values that make this true, and we're given a domain going from 0 to 2 pi. So I need to go around the unit circle one time and find the x values that work for this. Well, square root of 3 over 2 for sine is up here at pi over 3. Sine is also a positive square root of 3 over 2 in the second quadrant, so that would be at 2 pi over 3. So now that we have that, we need to find the y values that go with those angles. So for the first one, if I plug in a pi over 3, I get the square root of 3 times pi over 3 plus 2 cosine of pi over 3, and cosine of pi over 3 is 1/2. So I've got the square root of 3 pi over 3 plus 2 times 1/2 would just be 1. So that gives me my first point. And then there's a second point on this curve where we get a horizontal tangent line. So I plug in 2 pi over 3. So I'm going to get 2 times the square root of 3 times pi over 3 plus 2 cosine of 2 pi over 3. And cosine is negative in the second quadrant. So this is going to be a negative 1/2. And I end up with the point 2 pi over 3 and 2 times the square root of 3 pi over 3 minus 1. So both of these points would have horizontal tangent lines to the curve y equals square root of 3 times x plus 2 cosine x.